All right, so I want to now talk about some of the harder problems in this set. I only want to talk about three of them because the other two were significantly more difficult. And maybe actually, before I do that, let's look at the actual contest and the standings. This is in 2017 North Central North America contest. And of the 10 problems, there were two problems that were not solved by anybody in this whole region, despite a few attempts. And that would be Ruth Array and Atlantis. And because of that, I don't think there's a lot of point of me telling you how to do this because they're actually quite difficult. And maybe in this region, in our region, probably the result will be the same, that nobody can solve this problem. So I want to spend about time talking about the other three, which is stoichiometry A, Pokemon Go Go, which is B, and then this is has a where is it? Is it H or E? Is has a who knows A. Okay, then these problems, I think are definitely within your at least the more experienced teams. Perhaps I would say A and E are probably within the reach, and B probably is not too far. So let's get to it. If A has a who knows A. All right, so let's do this. Two familiar concepts in object-oriented program are the is a relationship, is a and has a relationship. Two classes, A and B. We say that A is a B if A is a subclass of B, and A has a B if one of the fields of A is the type B. Blah, blah, blah. So for example, here you have day extends times. So day is a time, and appointment is a date book. Appointment is a reminder, and appointment has a date. Okay, so that's the relationship is A and has A. These two relationships are transitive. For example, if A is a B and B is a C, then it follows that A is a C. This holds as well if we change all the is A to has A. So A has a B and B has a C, then A has a C. It also works with combination of is A and has A. In the example above, appointment time has a time, and since it has a day is a time. Okay, so appointment has a day, but because day is a time, so appointment also has a time. Similarly, if class date book has a year, then appointment has a year because appointment is a date book and date book has a year. In this problem, you'll be given a set of is A and has a relationship and a set of queries of the form A is or has A B, and you have to say true or false. Okay, there are at most 10,000 N and M. N is the number of is A and M is the number of has A. N is the number of is A and has a relationship. M is the number of queries. For each one, each of the relationship is something is A or something has A something else. And then the queries is always something is a something or has a something, you have to say true and false. Okay, and that's basically what you have to do. So basically what you have to do then is to figure out all the is a relate. So there are at most 10,000 of these things. So, and then they tell you that at most 500 distinct class names. So 500 is pretty small. And basically anything that is in the order of hundreds means that you can use an n-cube algorithm, right? So why is n-cube? Because a very simple algorithm called the Floyd Walsall's algorithm, there's many forms of this. One is to computing shortest, all pairs shortest path, but it's another form of this is to use to compute what is called a transitive closure. What is transitive closure? Transitive closure just means that once if you have a relationship, you compute all possible relationship if you allow transitivity to take into account. So if you know that A is a B and B is a C, then it will also know that A is a C. So what we're going to do is we're going to basically assume, of course, that you know how to convert the names of the different classes to an ID, to a number from 0 to 499. Okay, so you're going to have a table up to whatever number of classes you have, where okay, so you label all these, so is A, so you have an is A table that everything is just something of itself, so diagonal is 1, and then for each entry, ij is true if and only if class I is a J. Okay, and then you can have another table that looks exactly like this for has A, except that actually I don't remember if the diagonal should be 1 or 0. I don't think it should be 0. Nothing should be circular, and apart from the trivial identity, is a x is an x. Okay, so has A should have zeros on the diagonal, and then the ij entry is true if and only if I has a j. Okay, and then this concept closure, basically it's a piece of code that will turn this, that direct relationship that you get from the input, into a table where these entries are true if and only if I is in j, whether it's direct or indirect by transitivity. And similarly for hashtag. So you basically do this for it's k equal to 0, k less than n, k plus plus, and then I. So this is standard triple loop for Floyd-Warsaw algorithm. J equal to 0, j less than n, j plus plus, and I'll just write this as an array A, a Boolean array A, and you can decide whether you run the same code whether A is the is A array or A is the has A array, and just say Aij or equals Aik Akj. And this 4 lines of code will transform your array, your relationship from direct relationship to all transitive implications. So this is called concept closure algorithm. And of course, this is very clear that this is n cube time. And when n is 500, this is definitely good enough. How much time did they give you? There's the metadata. 3 seconds. So 3 seconds is plenty for 500 cubes. All right. So now that you know there is a has a, so what happens, right? If they ask you whether something is a something else, then the first thing then you just basically look up this table and see if the table says true or false. So it's a relatively simple lookup. Has a, well, you can also look it up, but there could be some difficulty when it says it's no. Okay, so why is it true? Why do we have this difficulty? Because, for example, if class A has a B, okay, and class B is a A, well, C has a B too, but this won't show up just here. So what you have to do is you have to ask, when you say, does C has a B, you have to say, well, first of all, does this maybe C has B? If you can look it up in this table and it says true, then immediately you know it's true. But it's possible that C is something that has a B. So what you have to do, if this is C, the row for C, you're going to have to look across this row. And then for each one of these items, you have to ask, if there's a 1 here, then does it also show up here? So what should I say? So for example, we can say for int I equals to 0, I less than n, I plus plus. They have mixed in code and these labels here. If C is a I and I has a B, something like this, then yes. Otherwise, no. Well, it's not quite, the L shouldn't be inside the if loop for a loop, but if you go through this whole thing and you haven't said yes, then you say no. So something like this, right? So you have to do a little bit of work to answer the query for has A. Is A, you never have to worry about going to the has A table, okay? Because is A is just completely answered in this table over here. So as long as you understand this, the coding should be relatively straightforward. Okay, there's two different types of closures, and then there's sort of one level of sensitivity, I guess you call it. You have to say C is a something, and then that something has a B. Okay, so altogether, you do n cube work to pre-process the data. If somebody asks you has A, then it's very fast to answer. You just look up the table, constant time. If somebody asks you has A, then you have to do a loop big O of n, which is not that bad. Okay, so that takes care of this one. Okay. Let's look at this stoichiometry. All right. So there's some kind of chemical reactions and blah, blah, blah. So you can read all of this. So for example, it says that there can be some kind of chemical reaction that says something like this. CH4, 2O2, CO2, H2O, and then in front of it there's these coefficients. So 1 of CH4 and 2 of O2 will give you 1 CO2 and 2 H2O. So the total number of atoms of each element on the left-hand side of the stoichiometric equation must match the number of that element on the right-hand side. Your task is to write a program that gives an equation of this form, so tell you what all the components are, but you have to figure out what goes in front to make sure that everything balances. And in this case, it turns out you put 6, 6, 6, and 1. Okay. An equation is input in the form of a sequence of at most 20 lines. One for each molecule of the formula, and each line has the following fields. The sign is either +1 or -1. A sign of +1 indicating that this molecule appears on the left of the equation, and a -1 indicating that it appears on the right. Okay. NM, which is between 1 and 19, is the number of element count pairs following the line. Each element MN is the element name because there are 1 or 2 uppercase or lowercase letters. Each count It's a positive integers from 1 to 12. For example, Fe2 indicates that the molecule contains 2 atoms of the element Fe. There would be no more than 10 unique elements in a single equation. Okay, so for example, an element may be repeated in any given line of input. So 1, 6, C. So plus 1 means that it appears on the left-hand side. There's 6 carbons, 1 hydrogen, 5, wait, I'm kidding. Sorry. There's 1 plus 1 is on the left, and there's 6 things that come. The first one is 1 carbon, then 5 hydrogen, another carbon, 1 oxygen, hydrogen. Okay. So that means that there are actually 2 carbons, 6 hydrogens, and oxygen. The program must output the numbers C1 up to Cm in order to fill in the blanks in the equation. Each number Cm must be the minimum number for which the equation is balanced. There's no common factor that could reduce all the Cm coefficients. You may assume that every input test case has exactly one valid solution meeting these criteria. All right, so what is going on? How are we going to deal with this problem? All right, so basically, I mean, there's parsing the input and all that stuff, and that most 10 elements, 10 different type of atom. And the idea is that for each type of atom, things must balance. Okay, the left-hand side and the count on the left-hand side must equal the count on the right-hand side. All right, so for example, what is the first equation, the simple one? That CH4 plus CH4 and O2, and then CO2 and H2O. So CH4 plus O2 gives you CO2 and H2O. And the question is, what is in front? Okay, so you're going to have kind of a constant. Let me use a different color so it doesn't look like it's another kind of, it's a lot of carbon atom. So you have some constant C1 times this much, and you have to figure out these constants. Okay, and you're told that there's only one solution that works if you remove all common vectors of C1, C2, C3, and C4. So whatever kind of solution you can compute, divide by the GC for all the coefficients, and that's your answer. Okay. So now, if we look at just basically how many different atoms do we have? We have, let me switch back to red. We have carbon, we have hydrogen, we have oxygen. And we look at how much each of the components contribute to this, right? So if you're looking at C1, however many of the first molecule you have, you contribute C1 of them. C2 doesn't contribute at all. C3 contributes one of them, and then C4 doesn't contribute any. So you can say that C1, based on this, C1 and C3 must be the same, or equivalently, you can write C1 minus 3C equal to 0. Okay. Then you do the same thing. C1 contributes 4 hydrogen. C2 doesn't contribute anything. And C4 doesn't contribute, C3 doesn't contribute any hydrogen, but C4 does. So 4C1 minus 2C4 has to be 0. And then finally for oxygen, C2 contributes 2, C3 contributes 2, and C4 contributes 1. So pretty soon you should realize that based on based on what we're doing, we would have a system equation. The variables, the unknowns of the equation, would be the coefficients here that you're looking for. And the number of equations you have here would be based on the number of different elements that you have. Okay. Now they tell you that at most a certain what the number of elements, blah blah blah. There will be no more than 10 unique elements, so that most 10 equations, and the number of element pairs, blah blah blah. Well, if there are those 10 equations, there could be more elements, I guess. So there are more things in the number of things. Yeah, there could be up to 20 different things that appear, but they also tell you that there's at most one solution, really. So what they're really saying is, if you think about this as a linear system equation, you have a certain number of unknowns, you have a certain number of equations, and that the solution space has rank exactly one. Okay, or the null space is exactly one. I guess you call it nullity. Okay. So what you do, I guess, you can solve the system equation and basically make sure that C1, C2, C3, all of those things are positive. That's important. You can't have negative. And they have no common factors. The problem, of course, is that if you do things the normal way, with a Gaussian Mason or whatever way you use to solve system equations, you can get fractions. And that may not be a good idea because you're not allowed to use fractions. But if you use an actual fraction class, that's not too bad because you can clear the denominator and get the integers. But if you use floating points, then that's bad because you might not be able to figure out how to multiply by the lowest common denominator, because from floating point you might have round-off errors, and even if you don't have round-off errors, you don't really know how to get the lowest common denominator. So the fact that they tell you that there's only sort of one solution really helps you. Okay, but anyhow, I want to show you the code library. So if you go to code library source, there are basically three different algorithms for solving linear system equations. The one that you should not use in this case, but I want to show you anyway because it might be useful in some other cases, linsolve.cc. And this solves systems of linear equations, and it solves ax equals b. So in this case, b is 0, a it would be whatever you form. And then you have to call this function. So this shows you how to do this. So everything is in double. So that's not what you want to do. But if that's your problem, then you do it. You set up your matrix, the coefficient matrix. You set up the right-hand side. Then you call something called LU decomposition with these parameters, and then you call LU solve to actually get the value that's unknown x. But LU decomposition could tell you that there's no unique solution. So in this case, you'll get no unique solution anyway, even without the problem of this the doubles. Okay, so anyway, this is not what you want to use, but I want to show you anyway, just in case it might come in handy later. Then there's something called FF linsolve, and this is what it's called fraction free. And the equations, the linear system equations, all the entries are integers, and then it will try to give you a solution that is not quite the right solution, but it will give you basically this x star, the solution that they give you, is actually the numerator of the solution. And then it gives you something called determinant A, which is if you know a linear algebra, that's the determinant of the matrix. And it will, if you divide every entry by the determinant, then that will give you the correct fraction for the solution. So in other words, it gives you the numerator and the denominator of the fraction. Okay. So that's kind of what we want, except for there's one problem. In the case where it's singular, so meaning that there's no unique solution, the solution vector is undefined. Well, so this is where it's quick. So what to do? Okay. We also have another one, and this one may be a little bit more obscure, called Diophantine-Cis. And this is the system of linear Diophantine equations. What are Diophantine equations? They're basically equations where you force the solution to be integers. Oh, okay, that seems like what we want. Given a system of m linear Diophantine equations in n unknown, the algorithm finds a particular solution as well as the basis of the solution space of the homogeneous system if they exist. So if you know linear algebra, if you want to know the solution, any solution of any system, you find one solution whatsoever, if you can find one, and then you solve the corresponding system where p is 0 and figure out all the possible solutions, and all you have to do is pick the particular solution and add any solution of the homogeneous system where the right-hand side is 0, and you get all the possible solutions of ax equals b. Now, in our case, p is 0, so that makes things a little bit easier. So actually, that's all you do. So you basically form this one. So you form a matrix basically based on what we talked about. P is just a vector of zeros. And then you call this function. The functions return the dimension of the solution space of the homogeneous system if it has a solution, otherwise it returns -1. So we know that the answer should always be 1. It should always return 1. Other results return in the parameters. xt is the n-dimensional vector giving a particular solution. And then the basis with the n by n matrix whose first dimension, whatever number of columns, form a basis of the solution space. We know that we only have one column to look at. But basically what happened is, with a homogeneous system, you'll probably get 0, the 0 vector as the particular solution. I'm not absolutely sure about this code, but probably that's what you'll get. And then the first column will give you a basis of the solution space, and basically to tell you that any multiple of the first column is the correct solution, because there's only one dimension. So in other words, what you do is you run this code. If xt is 0, which is what I expect to get, then you just look at the first column of this homogeneous basis, make sure that if all the entries are positive, if not, multiply by -1. The way it works, the way this problem is set up, either all of them are negative or all of them are positive. And then divided by the lowest greatest common divisor to reduce it, and that's your answer. Okay, so anyway, what are the takeaway? The first thing is, whenever we talk about balancing things and so on, especially because this problem is about equations, you probably want to set up system equations, right? Balancing every single type of atom. And then you have to realize that you only want integer solutions. And then you have to kind of look at the constraint of the problem very carefully and see which of the library code you can use. Most likely you want to use library code. Okay. All right. So that's this one. Only 2 teams in the actual contest. solve the problem. And then Pokemon Go. Let's look at this. Okay, so you have a bunch of Pokestop locations near the current location, as well as a list of Pokemon that can be found at each stop. The application then computes the shortest road one can follow to catch all the unique Pokemon and return to starting point. Program assumes that the users in the city where travel is restricted to moving only in north, south, east, west directions. Also assumes that all Pokestops on the intersection of two roads. For example, consider a case where the application finds 5 nearby Pokestops. Each stop location is indicated by 2 indices R and C. If your 5 locations are these 5, and the names of these stops are these things, then it's clear that one does not have to visit both second and third stop because they have the same Pokemon. So the best route is to visit first, fifth, fourth, and third stop, blah, blah, blah. And the distance is basically the sum of the difference in X in rows plus the sum of differences in columns. Okay, so input can hold a single test case. Okay, you always start at yeah, okay, so the rows and columns are the number of blocks north of your starting position and east and west of your starting position. So you basically start from 0, 0, and you have to come back to 0, 0. Test case begins a single integer n, the number of stops to consider, which is at most 20. Each of these n lines specify the location of a Pokestop and the name of a Pokemon that can be found there. The location specified by 2 integers R and C separated by a single space, blah, blah, blah. Location is followed by a string that's Pokemon 1 to 25 letters. Number of unique Pokemon is always less than or equal to 15. So even though you have up to 20 stops, you don't have 20 different Pokemon. You only have up to 15. Multiple Pokemon can reside at the same location, but are then listed as separate Pokestops. If the short distance in blocks required to catch all the unique Pokemon. All right. So let's imagine that every single stop has a unique Pokemon. Okay, so we'll assume for now that if you have 20 stops, you can actually have 20 Pokemon, different Pokemon. If you have that, then this is basically traveling salesman problem. And there is a very typical, I don't know what circle, but definitely for competitive programmers, a well-known algorithm, and I'm not going to say too much about this, a well-known dynamic programming traveling salesman algorithm that runtime is n squared 2 to the n. And the idea is that basically your state is what subset of vertices left to visit or has been visited. It doesn't really matter whether you look at the number of the subset of vertices that you still have to visit or you have visited. It's completely the same, whether you look at it one way or the opposite way. And also your current location. So you would basically be, wherever you are, you'll try to go to all different ways. Right? So wherever you are, you're going to try to go to all different ways, but you only go to the places that you haven't visited or you still have to visit. And then you recursively ask what is the best way to do it, and so on and so forth. And this is a pretty classical algorithm. And in our case, n is 20. So what? So 2 to the 20 and 20 squared. 2 to the 20 is about 1 million. 20 squared is about 400. That's exactly 400, so it's about 400 million. How much time are you allowed to use? 5 seconds. If I remember correctly, this is actually good enough. Okay. However, it might be just barely good enough. There's a better way to do this. And the better way to do this is that instead of keeping track of what are the subset of vertices you have to visit, you will look at what subset of Pokemon that you still have to collect. In that case, this will, instead of 2 to the n, will be 2 to the number of Pokemon, which drops this down to 15, and which makes it much faster. Okay, because they're basically dropping down 2 to the factor of 2 to the 5 or factor of 32. But if you understand that traveling salesman dynamic programming algorithm, then this is really the same thing. Right? At each location, you just go to all the different stops that still allow you to make progress. Don't go to any stops where that doesn't give you a Pokemon that you already that doesn't give you a Pokemon that you still have to collect. And if you do that, that will basically solve the problem. So I'm not going to write this out here, but you can definitely look it up. And if you run into any difficulty, if you really don't know, feel free to send me a message. I can show you the code to do that. All right. So I think that's all I have to say for these 3 problems. The other 2 are significantly harder. Hard enough that even if I know the solution and have the solution sitting right in front of me, it would still take me a while to understand what's going on. So I think for the regional contest in our region, the benefit of actually going through those 2 probably minimal. So I'll stop here.